there is also a global version of interpolating a function into a finite element space. So this also looks exactly like it did on one element because we have a nodal basis. And the nodal basis on one element implies a global nodal basis. And it's the obvious one. So our nodes are point evaluation. And so the point evaluation at a point in local coordinates just turns into the point evaluation of the corresponding point in global coordinates. And so if you have a degree of a node associated with a vertex, for example, then that vertex has a set of local coordinates, and the corresponding triangle in the global mesh has a vertex, and that vertex has coordinates in the global space. And that's all that's going on. So the same rule applies, which is if you wanted to interpolate some random function g into your finite element space, you would just evaluate the nodes at g. Well, actually, now we're in a little bit of trouble because mathematically we know what's got to happen, but we've got to practically make it happen. And thus far, we've only dealt with nodes which are defined on the local elements. And we're not going to change that. Everything we do in finite element space is only defined on the local elements. What we're going to do is define the change of coordinates that gets you between the local and the global space. And everything else you do is basically about change coordinates into local space, do the operation you know how to do in local space. It's the story of the rest of the course. So how do we do that? So there's a little bit of nomenclature here and a little bit of symbol conventions that you just have to wrap your brain around because it makes life easier. So we talk about physical space being the space on the mesh, because that's the thing that describes an actual physical domain that we're solving a partial differential equation over. And then local space is the space on one element. And typically, we use case to distinguish the objects in one and the other. So the local coordinates are big X, and the global coordinates are little x. I realize that seems like a reverse convention. It's not my convention. I'm not quite sure why the big space has little letters and the little space has big letters, but that is what quite a lot of the literature in finite elements does. So we are not going to invent our own convention for the hell of it. And similarly, so you'll have noticed that we typically use some of the Greek letters, phi and psi in particular, to represent basis. And when we need to specify that it's the local basis, we'll use capital letters, and if we were using the global basis, it's small letters. And the other convention that will become a little bit more apparent as we go on is when we are numbering basis functions, we tend to use the letters I, J, K, L, M, N if you need them. So letters from that set. So because there are other things that we have to number. We have to number geometric dimensions when we start taking gradients, and we have to number quadrature points. And so we have 3 species of index flying around, and if you use different symbols of the three species of index, it makes it vastly easier to understand what you're reading in the formula. So the convention is these guys are the those dimensions. So what we need to do, recall, is for a given triangle in the global mesh, work out the change of coordinates between the local space and the global space. And it turns out, as so often in this course, that we've actually already done this, we just didn't realize. And the reason we've already done this is because space itself can be represented as a finite element function. So the way to understand that is if you think about the triangle both locally and globally as being defined by its vertices, then what are the coordinates of any point inside the triangle? The coordinates of any point inside the triangle are the linear interpolation of the vertices. And if you take the linear finite element space, what does the linear finite element space do? it defines the linear interpolation between the vertices. So actually, there's just a finite element space for space. And that actually makes sense, because if you think about solving a partial differential equation, we deal in functions of space, fields you could call them if you like. And so these are things which associate a value with every point in space. So you can have a temperature at every point in space, but you could also have a vector value, like a velocity, at every point in space. And coordinates themselves just associate a vector with every point in space. It's just a vector field. It's a vector field that sort of points out from the origin and explodes out from the origin, but it is just a vector field. And so that's what we're doing. So actually, if you look at a particular triangle and you look at its local basis functions, and you take the global, small x, coordinates of the vertices, then the global point corresponding to any particular local point is just the global values of the vertices multiplied by the values of the basis functions at those points. So it's a finite element representation in terms of the local space. And we know the location of all the nodes in local coordinates. So there is a trap here. And the trap is that these guys interpolate, strictly speaking, not between the vertices, but between the nodes. And for P1, the nodes are on the vertices, but there's no guarantee that you numbered the nodes in the same order as the vertices are numbered. So you do have to be a little bit careful about how you do this. So we know the location of the nodes in local coordinates, because we wrote that down. And we have the tabulate method, which enables us to evaluate the basis functions of an element at a known set of points. So that works. And that just gives us this matrix, right? That's all the tabulate does. And so the global coordinates of the nodal points are given by that matrix multiplied by the global coordinates of the vertices.